Hi everyone, welcome to our lightning talk. My name is Tian. Along with me is Yinyu, Bo, Tianyi, and Xue. During this term, we have built a reinforcement learning model for taxi driver repositioning problem in New York City. So without further ado, let's jump right into the motivation part.
The goal is to optimize the decision-making of NYC taxi drivers using data science. Here we focus on reposition decision, where a driver should look for passengers to earn more per shift. In our project, we first explore empirical characteristics of the taxi trip dataset. This creates a baseline performance and a simulated environment, which is then used to evaluate our optimal policy that we learn using SASA algorithm.
The motivation comes from two parts. Firstly, there is a rising demand for improving traffic efficiency. For platforms, companies such as Uber and Lyft have increased the competition of the taxi industry, and cities are getting more congested. In Manhattan, the speed has dropped from 6 to 4 miles per hour, which is close to the working speed. The fierce competition and congestion make drivers spend about 40% of their time cruising and seeking passengers in the city. Also, drivers' earning is highly dependent on their decisions such as working shifts and starting time. Normally, there are two shifts for drivers in NYC, one morning shift and one evening shift. Figure 1 shows that drivers tend to earn more on weekends and evening shifts. Another important decision is repositioning. Drivers have to balance between the potential income and repositioning costs such as fuel cost and time. Our project will focus on this repositioning problem.
The dataset we used is the New York City taxi trip data. The features used in this project is the driver license, the pickup and drop-off date time, the trip distance, the trip fare, and the pickup and drop-off location. Due to computational limitation, we only used the yellow taxi trip records in June 2013, and we removed abnormal data based on exploratory data analysis of the features. For example, we calculated the average speed of each trip based on trip distance and trip time, and dropped records that have speed over 50 miles per hour, which is the highest speed limit in New York. Trips that are longer than 30 miles are also removed because they're about twice as long as the length of Manhattan. New York City is divided into 263 taxi zones. The taxi zones are meant to approximate neighborhoods, so you can see which neighborhood the passenger was picked up in and which neighborhood they were dropped off in.
Early data didn't contain zone ID, but only the coordinate latitude and longitudes of pickup and drop-off location, so we need to convert the coordinates to the ID. We speed up the process by filtering the zones first on if its bounding box contains the coordinates using our tree. Also, the trajectory of each trip is recovered as the shortest path between zones, weighted on distance for later use.
Let's talk methodology now. There are four key assumptions that we make in this process. So we discretize coordinates and time. The third assumption that we made is we treat this as a one-agent reinforcement learning problem. And the fourth assumption that we made is drivers can refuse rides. These assumptions will be really handy when we try to build up the model. So about our environment setup, there are four key elements in a reinforcement learning environment. The first one is agent, as we mentioned earlier, is one single driver. And the states, we define states as a tuple of location and time. So location is simply a taxi zone ID, and time is the discretized time. And for action, there are three types of action one agent can take: cruising, waiting, or repositioning. And the relevant reward consists of two parts: a positive reward for trip fare and a negative reward for all the trip distances that it has traveled. So let's use this as an example. So you can see here, this is the New York City. Let's say we are in Newark airport right now. So the first action that it can take is just to wait here, and there will be no reward. And the second action it can take is to cruise in this area. By taking this action, it will get a new order and it goes to another taxi zone, let's say it's here, and it will receive a reward, a positive reward for the trip fare and a negative reward for the trip distances that it traveled. And the third type of actions the agent can take is just to reposition to another taxi zone, let's say here. So by repositioning here, it can cruise in this area or reposition to another taxi zone here. The reasoning behind this is that maybe Newark Airport doesn't have much demand at that time, but downtown area has a higher demand. So by repositioning, it can gain a higher income. The training algorithm that we use is called SASA. So what SASA does is to estimate a Q function SA. So QSA is defined as taking action A at states S what will be the value the agent receives. And by feeding historical data into this SASA algorithm, we'll have an approximation of Q, and we can use Q to make a decision of what action it should take.
The first evaluation is the convergence of optimal Q values and the TD error. Q value is a number associated with each state action pair. You can think of it as the expected earning per shift for a driver who is in that state and takes that action. During the training, these Q values are updated by some amount known as TD error, and we expect the TD error to be eventually close to zero. Here are the results of our current model. The left plot is the optimal Q values that are averaged across all the states. The value levels off eventually after 10 million iterations. The right plot is the moving average of the TD error. The trend stays at around zero. The second evaluation is how better off a driver would be if they follow our optimal policy. We consider earning per shift and utilization rate, which is the proportion of worked hours with passengers to the total worked hours. The table here shows the empirical performance of both shifts. We are in the process of evaluating our policy performance. Once we finish, it will be compared against these numbers.
At each time interval, we can find the optimized policy of each zone to maximize the Q value. The action is shown as graph for each T, with red arrow representing travel to another zone, red circle representing travel within the same zone, and blue circle representing waiting in the same zone. One example is shown in the slide. We can find that there are many hotspots that are the ultimate destination of many other nodes. Some of them may be the special zones like 1 for Newark, 132 for JFK, and 138 for LaGuardia. Looking through the optimized policy at different time intervals, we may find that the percentage of zones that travel within itself is much higher during working hours, especially rush hours in Manhattan and Brooklyn areas. This can be observed more clearly by using the dynamic graph tool we implement by choosing different time. We may also zoom into Manhattan area to see the flow when the nodes are too close to each other in the whole map.
To conclude, our project built a reinforcement learning environment based on the estimation of some key values. Then we applied the SASA algorithm and get an optimized policy that drivers can follow. In the future, with more computational resources and time, we would be able to implement more rigorous estimations of the environment. For the algorithm, we can try other approximation methods. We also want to use more data to get a more generalized model. Thank you for listening, and you can click on the link to explore more about the project.